So today we are meeting after a long time, I think a week after. So I hope you enjoyed the Pauli festival and other festivals also. Since 2 days we could not discuss because of my bad health, but now today I'm feeling much better. Of course, maybe my voice that must not be clear, but I will try. So in the last lecture, we discussed about homomorphism and its properties. And today we are going to continue our discussion on a new topic called isomorphism. In fact, the definition of isomorphism we have already seen while discussing what is isomorphism. At the same time, we have seen this also. A few examples, maybe only one or two, we have seen what we mean by isomorphism. So in one sense, isomorphism is a particular case of homomorphism. In one sense, we can say. And on the other hand, we can also say that homomorphism is a generalization of isomorphism. So we know at that time, we know that any homomorphism which is 1, 1 and onto is termed as isomorphism. Okay. So what is homomorphism? Homomorphism basically was a thing structure preserving. Suppose we have two groups G and then another group G bar with the respective operation. Suppose here is operation composition operation is there, and this is operation, some star operation is there. So the G1 and G bar are groups. So in a homomorphism, what we see, we take some function from G to G bar and define it if phi satisfies phi of AB, in here operation should be the operation of G, and this should be equals to phi of A and star of this operation and phi of B. So if this structure is preserved, then we say that phi is a homomorphism. But in addition, if we have two more property, we can associate two more properties with phi. That is, if phi is 1, 1 and onto as well. Homomorphism plus 1, 1 and onto. Then we say that that function phi is an isomorphism. So if we want to relate what we mean really by isomorphism, so isomorphism is nothing but representation of the same thing in two or more different ways. Thing is that, okay. So if suppose phi G and G bar as isomorphic, then we used to write like this, that they are isomorphic. G is equivalent to G bar, like this, okay. You can understand this by means of example, what we mean by G is isomorphic to G bar, by taking some examples. Suppose you are writing 1, 2, 3, and 4 like this, and then you are writing them in Hindi 1, 2, 3, and 4, and here you write 5, then here you write 5, here you write 6. Sorry, this should be below. Like 6 here and 6 here, 7 here, and then you write 7 here like this, 8 here like this, and then 9 you are writing here, 9 here, and 10 here like this. So here you are writing 10. Okay. So thing is that these two number systems, if I say 1, And if I say ek, if I say two, if I say do, if I say three, if I say teen. So in this way, you will understand the same thing. If I say one or ek, so you will be getting, okay, sir is talking about one number. Okay, so it may be other language also, maybe French, German, Russian, or any other language, Persian. Okay, in India also, you may be having, we may be having we are having so many languages. So they are, in fact, if you say in Urdu, also they have their own way of saying what they say. 1, 2, 3, 4, 5. They have some name also. Just like we have alphabet, but thing is that alphabet has different meaning. We say in English A, here we say A, but thing is that sometimes they are equivalent, but thing is that you may not just translate that A be my A by means of A, you are saying A. Okay, but here these are the universal things. If you say one and you are saying ek, then you are meaning the same thing at both time. So this is isomorphism. Okay. So when we say that G is isomorphic to G is isomorphic to another group G bar, it means that there exists a 1-1 map from G to G bar, which is onto as well, and which is isomorphic as well. And these three properties, homomorphism, one-oneness, and onto-ness, will result many interesting properties. We can relate the elements of these two groups. Okay, so that we see later on when we discuss the properties of isomorphism. Just like we discuss the properties of homomorphism, we have seen so many things, if you remember. Okay, so similar properties will also be there. So let us see what is official definition of group homomorphism. So the same thing what I have discussed is written here. An isomorphism phi from G to G bar is a 1-1 mapping or function from G onto G bar. Okay, so here they are writing in language. Okay, but they are in assumption that 1-1, it should be 1-1 and onto as well, and that preserves the group operation. And this group operation we say in style. What we say that this is a homomorphism. Okay, so this is a homomorphism. We use some fancy language, fancy word for this homomorphism, and this is onto and this is 1-1. Okay, so if there is an isomorphism from G onto G bar, we say that G and G bar are isomorphic, and we write G is isomorphic to G bar. Is it okay until now? Hello?
Sir.
Okay. So here is a diagram. You can see that there are two groups G and G bar, and there is a map phi from G to G bar. So if you are taking two elements A and B, and this A is mapped to phi of A, B is mapped to phi of B, and of course because the G is a group, so their composition, okay, when we operate these two, A is like AB, then this will be mapped onto phi of A times phi of B. Okay, so this is a representation of homomorphism. And in addition, if it is 1-1 and onto, then we say that this is homomorphism. For better understanding, you can refer this table. If there is operation dot and G bar has operation dot also, then we this operation preservation we can denote like this. Okay, so here is the operation of G, group G, and here is the operation of group G bar. Okay, so if we change the operation, here is dot, here is plus, so we used to write like this. Okay, So similarly, if both are plus, then both at both places we are going to use plus sign only. So it is not like that we will be having only dot and plus. We may have so many operations, as we have seen in the starting, that using this dot plus we can define so many operations, okay, which are binary, and finally they also produces a group when they are associated with some sets, okay. So I think until now it is clear. Now it is time to have some example. Okay. So let us see example number 1. Let G is a group of set of real number under addition, and let us consider G bar is a group of positive real numbers under multiplication. Okay. Then define phi from G to G bar by how we can define there are real numbers, there are also real number, but they are positive real numbers. Okay. Here we are taking you should note that I have written here R plus. It means we are talking about positive, okay, non-zero real numbers. Okay, so let us define phi of x. X is some real number by 2 to the power x. Okay. Then we need to verify this is whether this is a 1, 1, on 2, and a homomorphism or not. And if all these three we are able to verify, then we can very much say that phi is a homomorphism. And one more thing you should note that this phi is not unique. Not unique. Okay. But thing is that if there is some phi from G to G bar such that phi becomes an isomorphism, okay, that is phi is 1, 1 onto an operation preserving, then we say that G is isomorphic to G bar. Okay. So it is not say that it is not like that that kind of phi which is 1, 1 and onto an operation preserving is unique always. Okay. So that we need to see. Okay, there may be so many phi. So that phi can also be counted, and that when we put together those functions, when we put together, suppose there is a phi 1, there is a phi 2, there is a phi 3, okay, suppose phi n. These are the functions from G to G bar which are isomorphic, okay, which are isomorphic. So how many isomorphism from G to G bar? There are exactly n isomorphism. Okay. So sometimes it is asked how many isomorphism from one group to another group is there. So there is another counting technique that we will see later. But you will get an idea from here also. Okay. So I am just defining phi of x equals to 2 to the power x. Then for 1, 1, yes. For 1 to 1, what we can say 2 to the power x equals to 2 to the power y. Okay. 2 to the power x equals to 2 to the power y. And you know that this is an infinite cyclic group. And infinite cyclic group, you know that if it is it holds, then x equals to y. Okay. If you remember the theorem. Otherwise, you can say you can write like this. This would imply that log of 2 to the power x and then 2 to the power x base 2 equals to, I'm writing this one, okay, 2 to the power x and a log of base 2 to the power y, and this would imply that x equals to y. This way also, but since this is an infinite cyclic group, you can write very much like this. Okay. Then onto how we can write onto. For onto phi of x, this is going to be mapped on some y, okay, or some y. And if it is 2 to the power x, but it is 2 to the power x, so we can solve this, okay, uh, so that each image has some pre-image, okay, each image should have some pre-image. So this should imply that x equals to log base 2 of y. Okay. So when we are writing phi of x equals to y, so for each y there exists log of base 2 y such that phi of x equals to y. So this is onto. And a homomorphism you can very much verify. I think you have done this when we were discussing homomorphism. You can write phi of xy, not like this, but you should see the operation here. Addition is there. So we cannot write like this. We need to write x plus y. So by definition, just use definition x plus y. Then you can write it 2 to the power x times 2 to the power y. Okay, and this operation is from right hand side. You see r plus under multiplication. So this is equals to phi of x times phi of y. So this phi, so this implies that phi is an isomorphism. An isomorphism. Do you have any idea? Can you define some more function from g to g bar in this example so that that function becomes a isomorphism? Any example? Any other function? Hello. Any quick reply? Yeah, please. Tell me. Can you define this like phi of 2 equals 5 to the power x? Huh? Hello.
Yes, sir, we can.
Or you can define this, suppose because r plus is nothing but positive real number, okay? So there should be naturally the natural numbers, all right? Huh? R plus,
Yes,
yeah. So can we write like this also? So corresponding to each natural number, we will be having this, okay? So there are so many function we can define over it, so that makes a so that phi is an homomorphism. Sorry, isomorphism. Every isomorphism is a homomorphism, but not conversely. Okay? Are you getting my point?
yes, sir.
Every isomorphism, because isomorphism is itself a homomorphism with one and onto properties. Okay, but not converse. So when we talk about homomorphism, it means we are talking about only operation preservation, like this. We are not very much concerned. We are not really concerned about its oneness or ontoness. Okay. Okay. Let us see next example. Example number 2. This is a most important example, and this is going to help in long run to all of you. And so many questions comes from here, so you should please remember this result. Any infinite cyclic group is isomorphic to the set of integers under addition. Okay. So how interesting this example is, you can see any infinite cyclic group you take. So you have a list of infinite cyclic group. Then you can say that they are isomorphic to Z. It means they have similar properties as Z has, set of integer has. Okay. So this is interesting. So we can take let G is generated by A, be an infinite cyclic group. Okay. So can you tell me the form of element G must have? What is the form of element G should have? E to the power k. Okay. Because G is generated by A. So this may be, if G is under multiplication, then we can write like this. If G is under addition, then we can say write like this. Okay. So without loss of generality, we can write like this. This belongs to G. Okay. This belongs to G. Now define some function phi from G to Z by how we can define phi of, because elements in G are of the form a to the power k, where k is some integer. Okay. And this is mapped onto k. Okay. Then phi is phi is an isomorphism. I think you can verify this. Huh? You can very much verify this is 1, 1, this is onto, and this is operation preserving also. Is it okay?
Yes, sir.
I think I should skip. Should I skip this?
Yes,
Oh.
sir, we will do.
Yeah, verify. What you can verify? You can verify. This is 1, 1, on 2, and operation preserving, that is homomorphism. Okay, these three things. This is very simple. For onto, if you are taking any integer, then obviously there is some element of this form, e to the power k. Okay, e to the power k should belongs to G. For any integer k, e to the power k belongs to G, such that k a to the power k becomes, this becomes a pre-image of this k. Let us take another example, example number 3. This is also important example. Or before going further, let us see some concrete examples for this. In fact, this is some result. This may come in form of some results and also. Okay, but let us say give some examples in support of this. So if we have the set of integers under addition, this is a group, our group. Okay, and we know that the subgroups of Z is this Z set of integers are of this form, and you know this. Okay, for any integer, this is a subgroup. Okay, this is a subgroup, and Z is a subgroup of Z. Fine, and Z is generated by, hello, Z is generated by Z is cyclic, infinite cyclic group. And what is
Cyclic.
generator of Z?
1 and minus 1.
Yes. And okay. So one more question. How many generators does an infinite cyclic group have?
Two.
Infinite cyclic groups has only 2 generators. All right. Do you remember?
Yes, sir, 2.
Yeah. So if one is a generator, then another generator is -1 in this case, in case of set of integers. Okay. You remember that 1 and a minus 1 are inverse of each other, because when we add them, they gives 0. Okay. So for example, if we are taking n equals to for example 13, so 13z also becomes a subgroup, and of course this is going to be a cyclic group. Every subgroups of cyclic group are cyclic. Do you remember? Hello. Every
Yes.
subgroup of a cyclic group is cyclic. I think this was a theorem, a fundamental theorem of cyclic group or something. Huh? So you have, if you multiply this by 13, so we have so many element dot dot dot, and then we have a, for example, minus 13. Just a minute. Every element of z multiplied by 13. So we have a 13 plus minus 13 plus minus 26 and dot dot dot. We have, and the generator of this is 13 and negative 13 both. Okay, you can see this one. Okay, so this 13z is also isomorphic to z. 13z is also isomorphic to z. Both have the same number of elements. Okay, and each element of 13z corresponding properties of each element of 13z is the same as the elements of z have. Okay, so this you can find it out. So many examples you can take. Other examples if you are taking which are with finite cyclic group, then that will be definitely is going to be isomorphic to z. So there are only one infinite cyclic group. There are only one infinite cyclic group. What is that? Z. Others infinite cyclic group will be isomorphic to this one only. They are not going to be different. Okay. So natural question is that what we can say about when the group is finite. Okay. So next result is about that only. I think example number, this was 2. Let us say example number 3. Example number 3. Every finite cyclic group is isomorphic to Zn. Set of integer modulo n. Okay. So any finite finite cyclic group they are talking about. Okay. So you know that Zn is always cyclic. Okay, Zn is so in sorry. Yes, Zn is always cyclic, and this says that there is a cyclic group of each order. जितना भी आप कहोगे 2021 ऑर्डर का कौन सा साइक्लिक ग्रुप होगा, तो आप क्या कहोगे? सर Z 2021 ये मैं लिख दे रहा हूं, और इस ऑर्डर का कोई भी ग्रुप आप देंगे ना तो वो इसी के आइसोमॉर्फिक हो जाएगा, बाकी मैं कुछ नहीं जानता। पक्का? कोई दिक्कत नहीं? हेलो हेलो।
नो सर।
या अगर आपसे कहा जाए कि 2021 ऑर्डर का फाइनाइट एक साइक्लिक ग्रुप बताइए, आपको जो फाइनाइट ऑर्डर का है तो फाइनाइट ही होगा, तो आप Z 2021 कह दीजिए, ठीक है ना? क्योंकि जितने भी साइक्लिक ग्रुप सारे बताइए। सर आप कोई सा भी साइक्लिक ग्रुप लेंगे ना इस ऑर्डर का तो इसी के आइसोमॉर्फिक होगा, इसका मतलब कोई से डिफरेंट हो ही नहीं सकता। ठीक है, ये बात अलग है कि हम उसका स्ट्रक्चर ढूंढ लें इस ऑर्डर का जो ग्रुप है, ठीक है ना, और हम ढूंढ लें, वो बात अलग है। लेकिन जो कुछ भी होगा ना पक्का इसके आइसोमॉर्फिक होने वाला है, ठीक है ना? हाउ इंटरेस्टिंग दिस वन। सो फाइनाइट, ये दोनों कितने काम के हैं हमारे? Zn है ना? अगर इनफाइनाइट साइक्लिक ग्रुप हुआ तो Z के आइसोमॉर्फिक हो जाएगा, अगर फाइनाइट साइक्लिक ग्रुप हुआ तो Zn के आइसोमॉर्फिक हो जाएगा, है ना? Okay, so how we can define operation on it? Okay, so let us see. Let us consider, let G be a finite cyclic group. Cyclic group. Okay, and let G be generated by A, some element A. Okay, define phi from G to Zn by. कैसे डिफाइन करेंगे हम? यहाँ के एलिमेंट a to the power k की फॉर्म के होंगे. So elements in G are of the form a to the power k. So phi of a to the power k is mapped to k, and because here is elements, these elements are considered under modulo n, under the operation modulo n. So we can write modulo n. So we will reduce this number. Okay, then phi is an isomorphism, and you can very much verify this. You need to verify this is 1 1, this is on 2, this is operation preserving. Okay, so in support of this, let us see some example also. So we can consider let h equals to 1 minus 1 and iota minus iota. This is a group of order 4. Do you remember? Is it cyclic? Is a generator of this, and you also know that a negative iota is also the generator of this. And then let us consider how this H can be isomorphic to some Zn. So let us consider Z4. So you can see 0, 1, 2, and 3. Okay. This is a group of order 4, and this is generated by, can you tell me some generator of this group? Hello. Generator of
Yes,
this?
sir.
What is, which element can generate this one?
1.
1?
Yes, sir.
Yes, sir.
I think you are forgetting everything day by day. What other generators could be there? 3 also, because 3 is inverse of 1.
1.
All right. 2 is self inverse. So let us see how this is their isomorphic. So let us define phi. But before that, let us see something interesting. Here I am. Let us write H and there Z4. Okay. So elements here, order of elements. If we see, okay, H has one element 1, and its order element and its order 1 का order कितना होगा? Hello, 1 is identity. Identity का order कितना होता है?
1.
Hello.
1.
Sir, 1.
1. So element 0 and order 1. ठीक. Element here, if you see, in H we have a negative 1. Its order is 2. Okay. So here we can find some element which order is 2, that is self inverse. I think this is 2. 2 plus 2, 4. Huh? So 2, its order is 2. Okay. And then we have iota, its order is 4. So here can we get some element which order is 4 in this one? I think one has order 4, and then iota is negative iota is also has order 4, and here 3 is also has order 4. Okay. So one element of one order, okay. One element of order 2, one element of one element of order 2, that is 2, okay. Two elements of order 4, namely iota and negative iota, and here also two elements of order 4, okay. So दोनों एक जैसे लग रहे कि नहीं लग रहे, है ना? बस notation different है, notation and operations they are different. So we can define phi from H to Z4 by how we can define. Do you remember that under homomorphism we have seen that identity map to identity? Okay, do you remember? So identity should be fixed. So 1 should be mapped to किस पे? 0 पे. ठीक, पक्का, कोई दिक्कत नहीं. Okay. How many elements are left? 3 more elements are left, and 3 more elements are also left here. How we can map them? We can map. Let us try to map -1, but -1 has property. -1 has its property. What is the property of this? negative 1 की property. It's order 2. So ये 2 order के element पे map होगा. So we can map it onto 2. All right. Hello.
Yes, sir.
Yes.
It has no choice, because if there would have more than 2 elements of order 2, more than 1 element of order 2, then there may be some choices. But because there is only 1 element of order 2, then there is only one choice. So what about iota? Phi of I. This should be mapped. There may be two choices. Either it may be mapped onto 1 or 3. Okay. Is it okay?
Okay, sir.
So if it is mapped onto 1, and then we have iota also, then this has also two choices, 1 or 3. पक्का, कोई दिक्कत नहीं? Okay.
No, sir.
So with this setting, what we can write. Suppose we are fixing it at phi I is equals to 1, and then we should have here 3. Another map we can define phi of 0 is 0. This is fixed. Phi of -1 should be equals to 2. This is also fixed. So another phi of I may be 3, and then in that case phi of negative I should be 1. So here we have two maps. Two maps. Which is 1 1 and onto. Clear है? 1 1 onto कहीं से clear हो गया है ना? पक्का? ऑपरेशन प्रिजर्विंग का चेक कर लीजिए आप. कोई भी नंबर उठाइए यहाँ का, कोई भी नंबर उठाइए यहाँ पे 1 and -1. ठीक है. So here should be multiplication in H, because H is under multiplication. Okay, fine. So phi of 1 and phi of -1. There should be plus. Okay, there should be plus and modulo 4. All right. So phi of 1 is what? 0. I'm considering this one. Okay. Of course, in this case, both, because these two are fixed, so this is applicable for both functions. So this phi of 1 is 0, and then phi of -1 is 2 plus 2. We have 2. Okay. Fine. This is 2, and is it okay? Hello.
Yes, sir.
Is it okay? So similarly, here if you see phi of 1 and minus 1, multiplication of these two will give what? -1, and -1 is mapped to 2. दो आया है यहाँ पे, तो लेफ्ट हैंड साइड ये भी 2 है और राइट हैंड साइड कंप्यूट किया ये भी 2 आ रहा है. पक्का, कोई दिक्कत नहीं. ऐसे ही आप you can make so many pairs, available pairs. You can take -1 times iota. So in fact this is equals to phi of minus iota, and this phi of minus iota is 3. So this would be equals to 3. Let us see phi of minus iota, and then no, this -1, and then so phi of -1 by definition is 2. So this is 2, and here it should be plus, and plus what? Iota. This is equals to 1. So this is equals to 3. You see, 3 is also here, 3 is also here. Okay.
Okay,
Hello.
sir.
So similarly, you can verify other things also. One more thing. One more thing we can think of. Can we map phi of -1 to 3? Because we have seen that we have defined this kind of map because order of -1 is 2 and order of 2 is also 2. So that's why we fixed this one. But in case, for example, if we define phi of -1 equals to 3, पक्का, कोई दिक्कत नहीं. And in this case, phi of minus I, if we are defining this is equals to 2, then in this case what happens? Let us see. So let us consider phi of -1 times iota. So this is phi of minus iota, and this minus iota is equals to this is equals to 2. I think this is equals to 2 with another definition. Okay. And if it is operation preserving, then phi of -1, phi of I. So phi of -1 is here we see 3, and I is 1. Phi of I is 1. Okay. Sorry. This is 4. This is equals to 0. But it should have been 2. Okay. Do you understand? Sorry. Are you getting what I'm trying to say? So
Yes,
this
sir.
definition is not valid. This definition is not valid. This definition is not valid. Okay. So we need to see first. पहले जब दो फाइनाइट ग्रुप आए तो आइडेंटिटी को आइडेंटिटी पे मैप कराना है, और फिर we need to see order of elements and what they are, and then accordingly we map. So there are essentially two. How many operations, how many isomorphism we got here? 2. Sorry, how many function isomorphism? तो यहाँ पे कितने isomorphism मिले हमें? 2 isomorphism from S to Z4. From H to Z4. Okay. So with this, let us conclude discussion for today.
Thank you for watching this video. To stay updated, please subscribe to our YouTube channel, Cosmos Learning. Happy learning through Cosmos Learning. To watch more, click on any of these cards. Thank you once again.